Hello, everyone, and welcome to this live tour today of LVV, the Laboratory of Verification and Validation. I'm Nikos. If you want, my full name is Nikolaos Dervilis, and I am a professor in Mechanical Engineering and the Dynamics Research Group. And together with Keith Worden, who is also a professor in Mechanical Engineering and the Dynamics Research Group, we will travel together across the lab today. So first, I'll give you a quick introduction, a quick fast one about a teaser about the lab, a little bit about the Dynamics Research Group quickly. And then I will hand over to Keith that will guide all of you live across the lab. So welcome again. LVV stands for, as you can see, for Laboratory of Verification and Validation across scales and environments. And I'll give a little bit of context in a bit. The LVV was funded as part of EPSRC, as well as the University of Sheffield and the European Research Development Funding, ERDF. And so it is a research facility that is made to test large structures. It's a lab that envisioned to be a world-leading lab in structural dynamics, and what the group wanted and envisioned is to have a lab that we can test across different environments, different dynamic conditions, different boundary conditions, and to help a lot to validate physics-based models. And this verification and validation procedure is really important across the design processes, and it becomes even more important now when we're looking into digital twins, when we're looking into extrapolation, when we're looking into how we combine data and physics. So this lab is critical even more now when we are testing structures, and especially structural dynamics. Now, this lab was envisioned and was led by the Dynamics Research Group, based on in mechanical engineering, a group that has a life over 30 years now, and it is one of the world leading groups in the world in dynamics. It sounds like a sales pitch, but just to give you background about the Dynamics Research Group quickly, is a group that has a lot of expertise in structural health monitoring, so how we assess the health condition of a structure, the same way you would assess the health of a human, how we assess that for a structure. We're looking a lot on system identification, so how we extract information from data, and we try to fit that information to models, as well as a lot on nonlinear dynamics and acoustics, as well as control and damping. So it is a really large group. It compromises of around 12 academics, and we have over 50 postdoctoral researchers and PhD students. And over the years, we had secured a good chunk of funding, and we have a really strong collaboration for over 25 years with several international partners, but a lot with Los Alamos National Laboratories in the US, and especially the Engineering Institute and Chuck Farrar. who is the director of the Engineering Institute. Here are the DRG academics. I will not go through all of them, but you can see the names and everyone. And of course, the LVV team. And there, I will go through the names because they are essential people for the LVV. Robin, Charlie, and Michael. The director of the LVV is Keith Worden, and the other co-director of the LVV is Lizzie Cross. So this is the teaser for the lab. You can see, you can have a live tour, a tour of the lab through a virtual environment. So you can go to the LVV web page, you can click the Explore 3D space, and you can go through the lab and what are the capabilities of the lab for anyone that want to have a look. You can see the chambers, which Keith will talk more, the wave tank and the strong floor here. And here is a better zoom point of the chambers. So these are environmental chambers, and this is something that, as Keith will explain, very unique in the world, because not only we can do structural testing in the chambers, but we can also test the structures at the same time with different environmental conditions. And this is quite unique in the world. Here is one of the main chambers, which has a shaking table. Now, there are a lot of labs that have shaking tables. There are not a lot of labs that can have shaking tables within environmental chambers. And this is a very, very important capability for Sheffield, for UK, and for the world, I would say, in terms of structural dynamics testing. We can make the chambers rain as well at the same time. We can change the temperature through various degrees, and Keith will give more information. We can change the humidity. We can ice them. We can blow wind inside the chambers. And obviously, we can do big structural vibration testing and ground vibration testing. So here, you can see multiple sensors and shakers attached to this aircraft, and how we can do a full structural analysis of a whole aircraft of this size. And obviously, you can see as well as the wave tank as well, where we can circulate different modeling of waves to do scale testing in the wave tank. Here you can see some more information about the capabilities. As I said, the environmental chamber. We can control the temperature. We can have hydraulic multi-axis testing capabilities. We can make it rain, wind, and we have large electrodynamic shakers as well. So this is essentially what I just described at the beginning. What I want to point out, and we want all of us to be clear that this is a lab that we are really looking forward all of you to come and test in the lab, use the lab. It's free for a collaboration, and I think this is one of the big benefits we want to come across today about the capabilities of the lab, and looking forward for people to have and come and look and use the lab. So this is some grants at the moment that support the lab. A lot of them recently have to do with digital twins. There's a lot of grants with the PSRC and the Alan Turing. We have a big program grant like ROSIPS that looks into populations for structural health monitoring, as well as some leading grants in acoustics and aeronautics, like landing gears, as well as fellowships and that support the lab at the moment as well. And of course, this is research grants, but as you've seen in the beginning slide, there is a lot of industry at the moment that is using the lab, like Siemens, but also AMRC has a lot of collaboration at the moment with the LVV. So I think I'll hand over to Keith now. So Keith will start the journey, the life journey across the lab.
Okay. So you can see at the moment we're standing outside the main entrance to the laboratory in the office area at the front. We're going to go into the business end of the lab now and work through a series of different demonstrations that are intended to show the capability of the lab, which has, as Nikos said, is quite unique in many respects. To the right of us there, you can see there's a workshop area. This is essentially so that we have the capability to manufacture any fittings or rigs, fixtures that are needed for testing on site, so that we don't have to outsource any day-to-day operational requirements. So now we can walk to the first laboratory capability and the first demonstration. So you can see in front of you a strong wall. This is designed really so that we can cantilever off some fairly substantial pieces of equipment in order to do dynamic testing, and it's sitting at the end of an area of strong floor as well, which we can see here. We can attach to the floor and the wall any number of structures for vibration testing. The one that you can see at the moment, the one that is oscillating in front of you, is a helicopter blade, which is a composite helicopter blade. As Nikos mentioned, we have a number of grants in operation at the moment, and this one is related to a grant on population-based structural health monitoring, where we've been testing multiple copies of structures in order to see if we can transfer information between them. This particular test takes things a little bit further than the usual diagnostics that we do, and it's intended to look at prognosis. Can we predict the progress of damage in a structure? So as you can see, this is under a fatigue test at the moment. In order to get large oscillations, we're not using the electrodynamic shaker that you can see there. If we go to the left a little bit, you'll be able to see under the blade a mechanism which contains a rotating eccentric mass, and this allows us to get large amplitude motions on the structure at a range of frequencies. At the moment, this is running at about 2.5 to 3 hertz in the second mode of vibration of the structure. So if we look at the root of the blade, you can see that we have the section there instrumented to acquire a number of different types of data. So the larger sensors there, the cylindrical ones, are accelerometers so that we can record vibration data, and the smaller sensors are acoustic emission sensors so that we can extract transient ultrasonic waves. The idea of this experiment is that in the center of the region you can see there, we'll initiate a crack and then we'll continue to monitor the structure as a fatigue crack grows through the route to final failure. Prognosis is quite a lot more difficult than diagnosis because we're going to need to know a great deal about the physics of the damage progression. So a mixture of structural health diagnostics and prognostics here, the main feature being the strong wall. If we turn now and walk a little into the center region of the lab, what you can't avoid seeing is this aeroplane. So this was a gift from DSTL when the lab was commissioned. It's an ex-Red Arrows jet aircraft. It is decommissioned. The powertrain, drivetrain has been removed, along with one or two other parts of the aircraft. But what remains is the entire airframe from a structural point of view. And what is happening to this aircraft at the moment is we are recreating the conditions for a ground vibration test, which is one of the fundamental processes that any new aircraft must go through. And this will establish the vibration characteristics of the aeroplane in such a way that the measurements can be used to update finite element models or any predictive models that we want to use. To get a fully comprehensive picture of the vibration behavior of the aircraft, we need a lot of sensors. You can see there on the wing, there are quite a lot of accelerometers, lots of different channels there. And the fact that we have quite a dense sensor network means that we can measure the patterns of movement, the mode shapes of this aeroplane with quite a high resolution. The excitation here, in order, as I say, to map out the full behavior of the aircraft, needs multiple excitation points. And so we have a number of electrodynamic shakers attached. Here we can see one underneath the wing, but there's one under the other wing and there's one on the tailplane, which can be used to give a horizontal excitation. This is a very important test in the development of new aircraft structures, and so we're developing the capability to do a full ground vibration test within the laboratory, a full multi-shaker test. We have industry standard modal analysis equipment, which we'll see a little bit later. So there she is, that's the Hawk. If we turn now, what we will see is a set of 3 environmental chambers, and these are really the centerpiece of the laboratory. This was the result of an application to EPSRC for strategic equipment funding. And in order to justify that investment, we had to create a facility which is unique in the world, really. And as Nikos said, there are other environmental chambers and there are other shaking tables, but there aren't any shaking tables inside an environmental chamber. We'll get to that in a minute. This is chamber 1. It's one of the larger chambers. It's the footprint is 5 meters by 8 meters and it's 4 meters high. We can get a temperature range in between -55 and +55, which has been designed for aerospace needs. And we can get humidities between about 10%, 80%, relative humidity. As Nikos said, we can make it rain. There's a rain gantry there. It looks as if there are 8 taps attached there, but actually these things have been designed so that they can generate a good spread and will generate a realistic rain field across the area of a structure. Now, if we step back a little and look to the left, what we have here is a 10 kilonewton electrodynamic shaker, which can be used to produce substantial forces up into the tens of kilohertz. The cardboard box on the top is covering a sample which is commercially sensitive, so we are being careful about that. If we move forward a little bit, and on the left, what we see is an icing system which was designed and put together within the laboratory by Robin Mills and Mike Dutchman. And the geometry of it at the moment is designed to induce ice on the leading edge of a helicopter blade, icing being a problem for helicopter dynamics and performance. To the right of that, you can see we have a very big fan here. This can generate winds of up to 50 miles an hour over a quite substantial cross-section. We can't generate full wind tunnel capability because we don't have the necessary boundary control. But for the purposes of our tests, which is to create environmental conditions, that is perfectly good for generating a lot of the wind fields that we would like to use. If we step back a little, we can see again examples of some populations of structures that are being tested for health monitoring purposes. The one immediately in front of us is an example of an aircraft benchmark structure called the Garter structure. If we look a little closely on the right wing there, well, the left wing, the way we're facing, you can see that we've actually introduced some damage in the form of a saw cut. And the object of the exercise here is that we can locate and size damage within the structure. We have multiple copies of this Garter aircraft in different sizes, 2 aluminium, 2 steel, 1 brass, 2 wooden, and here is one of the steel structures that's on the same scale as the aluminium aircraft. And again, the emphasis here is on transferring health information between structures, which is something which is a very recent development in structural health monitoring technology. Now, if we move into the chamber to the right of this chamber, this is sort of the pièce de résistance of the laboratory. We have another big chamber, 5 by 8 by 4 high, and it contains a full 6-axis shake table. The shake table has a travel of about 100 millimeters, and it can move a 1-ton mass at accelerations up to 3G. And it has a frequency range of about 5 hertz to 100 hertz. It rolls off outside that range, which is why we've got some big electrodynamic shakers as well. You can see on the mast at the moment, we have something which we call our modular bridge kit, which is like a big Meccano set for creating realistic bridge structures. This is configured at the moment to look like a 3-span bridge where we have the data from the corresponding real structure. And we can introduce ground vibration into this bridge, and we can create different temperature, humidity, and wind environments for it. One of the interesting things about the shaker is that the mast, when it is moving through its full travel, creates such a large change in volume that we would lose accurate temperature control if we didn't compensate with that. And so you can see there's a large diaphragm in the roof of this chamber so that we can maintain constant volume and therefore maintain accurate temperature control. So if we go into the final chamber, what you'll be able to see, this is a smaller chamber. This is a 5x5 footprint, but still 4 meters high, has the same temperature, humidity, rain capability as the other chambers. It's useful to have a smaller one because there is less energy consumptions to control the environment if you have a smaller structure. And what we have in here at the moment is an experiment that is looking at thermal batteries, essentially. So that's the final chamber. And if we now leave, what we see is another set piece of the laboratory. So this is a wave tank. The wave tank was provided for us by the ERDF funding component for the laboratory, among other things. And it is there to allow us to do fluid structure interaction experiments, which are important for us in the context of things like offshore structure dynamics, and then following on from that, offshore structure health monitoring. You can see that the structure in there at the moment, this vertical cylinder, is simulating a monopile construction wind turbine tower. This is quite a powerful capability, actually. We can control the wave kinematics to produce pretty much whatever surface wave spectrum we like. At the moment, what we're seeing here is a John Swap spectrum, which means that we're reproducing the conditions in the North Sea. But we can create periodic waves, we can create breaking waves, and the tank will recirculate, and we can produce tidal behavior as well. There are 2 actuators at each end of the tank. At the moment, we have one that is actuating and the other one is essentially receiving. If we go up the steps, we'll be able to look down and see what the footprint of the tank looks like. It's 12 meters long and about 50 centimeters across. It's been designed to produce unidirectional waves, unidirectional plane waves for these sorts of experiments. There we can see one of the paddle actuators. And in this particular case, this is what is driving the wave motion. As I say, complete controllability of the kinematics of the waves. And we do have some facilities for flow field visualization that have been developed in-house as well. So there you can see the controller. Now, if we move back to the main laboratory floor, we're nearly at the end of the tour now. If we move around, we can see some of the general equipment that is part of the laboratory's capability. Of course, we can do all of the standard vibration testing that you might expect from a dynamics laboratory. We can see some of the equipment here. We've got a couple of point laser vibrometers there. And to the right there, this is an industry standard modal analysis kit produced by Siemens PLC, which used to be LMS, Leuven measurement systems, and they have been the standard, arguably, since the 70s. If we look a little more to the left there, we can see some of the signal conditioning modules, one of the smaller shakers, and a little further to the left, we have a scanning laser vibrometer. So there is the scanning head from the vibrometer, and what it is doing at the moment is it is doing a full field vibration assay of that composite plate. That composite plate is a glass fiber plate, which is typical of marine composites and the sort of thing that could be found in wind turbine construction. And that is a piezoelectric stack actuator there, which is driving the waves. The vibrometer itself can actually do a full field measurement up to 20 megahertz or megasamples per second, which means that we can get well into the ultrasonic wave regime as far as out of plane measurements are concerned. And I think there we have it. I think we've seen all of the main features of the laboratory. I forgot. Sorry. If we look up on the gantry, this is another of our structures, another gift from DSTL, to whom we are very grateful. This is a Lynx helicopter airframe. It's the full airframe without the drivetrain, essentially, or without all of the ingredients of the drivetrain. And this is a mixed metallic composite structure, which is extremely useful for carrying out fundamental research on structural vibrations. And I think there we have it.
So I think we can do some Q&A now. If anyone has any questions, I can see in the chat that we have a couple of questions. Niriana, I don't know if I pronounced your name correct, so I apologize. So the question is, one of them is about the environmental conditions control. I don't know if we have answered that already, but yes, we can control the humidity and the temperature and the wind speed. Keith, I'm not sure about the intensity of the turbulence.
Not directly. As I said, we don't have a full wind tunnel capability here, but obviously by experiment, we can generate intensity of turbulence across a range of across a range, and we can do that by adjusting the speed of the wind fan, and potentially by controlling the scale of any of the models that we might test in the laboratory.
And there is another technical question about the centrifugal blower on the wind.
Okay. I'm not altogether sure about what the specification of the centrifugal blower are. As I say, we can generate a wind field of well, the cross-sectional area of the face of the fan at speeds up to 50 miles an hour, and we can control that quite accurately.
But we're happy to check for more details if needed. So just drop us an email or to Charlie, as you can see, and we can come back.
The fan is off the shelf, so we can actually probably give detailed specifications for that.
Yep.
a number of, obviously, as you can see, a great deal of the stuff inside the laboratory is bespoke. It was either put there at construction, or capability has been introduced by Robin and Mike over the years. But the fan, yes, we can probably give a specification for that. Just out of interest, one of the things that I forgot to mention during the tour was that there is a 300-ton seismic mass under the shaking table, which is actually sitting on top of pneumatic isolators. And what this means is that even when the mast is going pretty much at full tilt, there is no vibration transmission into the rest of the laboratory, which is obviously really useful for us, but it's also useful for our neighbours, some of whom are running electron microscopes.
Are there any other questions? Yes. Do we still have the material fatigue testing machines except the shakers in the building?
So we don't have any fatigue machines in the laboratory. The fatigue machines that we use for research and for consultancy purposes are in the main mapping building, either in the Lee lab, the Swift lab, or the Dynamics Hot Space lab. And there's a range of fatigue machines available there, covering a range of loads and capabilities.
But for the helicopter blade, you've seen the fatigue test that Robin created it here, so it can accommodate our specific helicopter blade fatigue testing that we wanted to do.
Yeah, the eccentric mass really. Some people may have seen a full-scale wind turbine test with an 80-meter blade. They are quite spectacular, and they tend to use an eccentric mass exciter because it's the only way to get a really large periodic force into these structures. So ours is a very, very tiny cartoon version of that.
So we have another question. What do you usually test in the water tank? Well, as Keith said, we test a lot of we're doing a lot of testing so we can understand the wave loading that goes into offshore structures. So we're trying to find out what is the wave loading and the forces on offshore structures. And we are testing at the moment a lot of offshore monopile structures, but we're also, as well as some floating structures as well, especially for floating wind turbines. So it's a lot of to do with the structural dynamics, which are very complicated in offshore platforms when you try to interpret what is the wave force in order to fatigue cycle analysis, and especially when it comes into the nonlinear regime, how you calculate the forces.
To one experiment, which is just waiting to go into the tank, is looking at an array of monopile structures. And the idea will be that we will look at variations in the foundation conditions and ultimately develop the technology to detect scour changes in the foundation conditions.
Do we have any questions? Or if you haven't answered any of your questions properly, please follow up. As I said, if you have any more questions, you can see on the slide. You can contact Charlie, who is the lab business manager, and we'll be happy to follow up with any questions or queries you're having, of course.
We also have quite a large laboratory within the mapping complex, the Heart Space laboratory, and that has a full vibration test capability as well, modal analysis, and also has some interesting structures. We've got a very small but complete earth airplane in there, and some interesting models of suspension bridges and more versions of the garter structure. Some rigs for condition monitoring research, including some quite modern burying rigs shared with the tribology department. So there's quite a lot going on within mapping as well. So if anybody is around the mapping complex and would like a little look around the Heart Space Lab, then you can give us a shout about that as well.
All right. I think we would like to thank everyone. Thanks so much, especially that you're here during lunchtime. And we're looking forward to hear back from you. And as I said, if you have any queries, just drop us out to Charlie. All the details are on the slide. Again, thanks so much from all of us, and thank all the people that put that together today. So thank you all, and have a great day.